Okay, so I will be talking about exoplanets. Exoplanets means, the planets around stars. Those stars can be sun-like or little different from sun, but basically planets around other stars are known as exoplanets. So how do we detect them, and why their detections are so challenging? So, like if you look in the night sky, you will see different stars in the sky, right? And traditionally, an astronomer, what he does is that uh, he or she will actually point the telescope towards the star, and then like collect photons from the star. And with photons you can do two things: you can do spectroscopy or photometry. When you count the number of photons coming from the star per second, it's called photometry. And when you do uh, when you analyze the distribution of photons with respect to their wavelength or frequency, it's called spectroscopy. And so with these two analytic tool, you from photons, using photons, you can actually derive all the physical parameters of the stars. Okay, and that's how the astronomy, the subject of astronomy was developed. When I say physical parameters, I mean the mass of the star, the size of the star, how far it is from us, and how old it is, what are its composition. Practically everything you can think of any physical matter, you can actually find out about the stars, even though they are very very far away from us, many light years away. Okay, now what about planets? The issue with planet is the following: is that if you look at this curve, you can see that the red curve. This is the star black body curve, and this is the the intensity. And so say if you say that if you say, take an example of a say alien creature which is like even 30 light years away from us, from our solar system, in a spaceship trying to figure out whether there are any planets around stars around the sun or not, he will be a hell of a time to figure that out. Because you see, if you see the contrast between the sun's brightness and the other planets' brightness like Jupiter, Venus, Earth, Mars, and other planets, you can see the difference is very huge. In case of Sun, Jupiter, the contrast is like 1 billion. And in case of Sun and Earth, the contrast is like 10 billion. Okay, so which means that, you cannot actually image the planets that goes around the star, because they are so faint compared to the star, and they are so close to the bright star. It is like, trying to see a firefly against the light of a lighthouse. So that's the problem. Okay, so how do we solve this problem? So luckily, like physics and science obeys nature's laws, and because they obey nature's laws, using those laws of physics, we can figure out whether there is a planet around a star or not. Okay, so here is another example that, like you can see that when you talk of contrast of 1 billion or 10 billion, it is like, like seeing something as faint as this, where my cursor is somewhere here close to the star. So typically you can see it's not possible. So this is some kind of an example of image I was trying to show you. Okay, so now exoplanet detection techniques through indirect measurement. So as I told you, the direct measurements are very difficult, although there are some direct imaging being done now using high contrast chronographic imaging. I will not go to that because that is in a very very initial phase where we can only achieve like 10 to the power of -8 contrast, whereas I told you that if you want to detect sun Jupiter kind of system, then you need like something around 1 billion. So we have not reached technically 1 billion, but maybe in next decade or so we may be able to achieve. So I will now in this talk mainly focus on indirect techniques of measurements by which we can know whether there is a planet around the star or not. First is uh, the uh, the astrometry, then radial velocity, then you have the transit, and then you have the gravitational lensing system. So I will go in the reverse order. I will try to tell you first what gravitational lensing is, then I will go to transit, then I will go to radial velocity, and then I will go to astrometry. And in this talk, mostly I will focus on radial velocity and transit. And in the beginning, I will talk about gravitational lensing and astrometry. So what is gravitational lensing? You see, light behaves as a particle as per Einstein's theory of general theory of relativity. So when you have, like two sources, like you have the source and you have the lens. I mean the matter, when the light passes very close through, grazingly pass through a body, massive body, it bends. So as it is shown here, that you have a distant star and you have another star here, and this is your its actually influence, and so you can see that the starlight goes like this, it bends and goes to the observer. From here it goes like this and bends and goes like this. Okay, and the direct light goes like this. So basically, which means that it will see a sort of a distorted source because of this uh, this uh, this gravitational lens. This gravitational lens is nothing but one star, another star, foreground star. This is the background star, and this is the foreground star, and this is the observer. That is us. Okay, and typically, like this angle of deflection alpha is defined by this, where you can see that the mass of the lens, that is the mass of this lensing star, is coming to the picture. G is the gravitational constant, c is the speed of light, and this zeta is the distance. This distance, that is the minimum distance from where the deflection is happening. Okay. Uh, so how do you using this technique, how do you actually determine whether there is a planet around this lens is there or not? Okay, the idea it goes like this, is that in this video I will show you where this is a background star, this is a foreground star, and this foreground star has a planet around it. So I will put this video. As you see that the star comes within the this thing, you can see that as the star is approaching this thing, the light is getting bent, so the intensity of the background light is increasing. This shows the intensity of the background light. Okay, is increasing, and as it increases, and then because of, sorry. So you can see that as the planet goes in front of this, it sees it makes a small kink here. Okay, so the presence of this small kink here actually shows there is a planet around this star. Okay, this is a very crude way I showed you. There is a lot of mathematics involved. So so this is actual observations. So what happened on this particular source here, and you can see that it increases and it's gone down, and then there is a small kink here, and this is a zoom up picture of this, and this whole thing even took into happen in the days of 40 days or something. Okay, so and the mass of the planet was calculated to be 5.5 Earth mass. Okay, and the distance between the star and the planet was found to be 2.6 AU. Okay, this discovery was done in 2005. So this is the way, one of the way to detect indirectly, a planet around a star. However, this is purely serendipity, because you don't know like when there will be a star. You don't know when there will be a star, foreground star passing through a background star, and whether that foreground star will have a planet around it or not. So, like you observe this for many months or many years, maybe you will find 10 such sources. So this is not very efficient way of finding out planets around stars. Okay. So we will go to the next method, which is the transit method. Now, you have this, we all know that eclipse, solar eclipse, lunar eclipse, right? So, so how does this happen? That because the moon comes in between us and the sun, and then it blocks completely the sun, and therefore we see the corona and the solar eclipse happens. Similarly, the sun the earth comes between moon and the sun, and so in the night we see the lunar eclipse. And because the size, by strange coincidence, even though the moon is very small compared to the sun, and earth is very small compared to the sun, it so happens that the distance between sun and earth and moon, and so that they sustain the same angle on us. So therefore the moon completely covers the sun, and the earth completely covers the sun, casting a total shadow on the moon, and that's why we have total solar eclipses and total lunar eclipses. Now consider a situation where you have like a planet going in front of the sun, in front of the star, its host star, and that plane coincides with our plane, observing plane. So then in that case, what will happen is that the star will extend a very small tiny angle to us, much smaller compared to the sun, compared to the star. So therefore, that the planet will sustain a very smaller angle compared to the sun, compared to the star. So therefore, what will happen that only a tiny portion, as shown in this cartoon, a tiny portion of light it will block, as we are constantly doing photometry of the star. So you will see a dip here. You can see a smaller planet going around gives a smaller dip, and the larger planet going around, it gives a larger dip. So therefore, like with this, you can say that, okay, some planet is going around the star, and the probability of such a thing happening is less than equal to 2%. Okay, but still it is much greater than microlensing events. Okay, so therefore it is comparatively more efficient than microlensing events. So as is you can see the drop of the intensity is proportional to the radius of the planet to the radius of the star. So the r square by r square, where small r is the radius of the planet and the big R is the radius of the star, you can, from this ratio, you can actually figure out the radius of the planet. Okay, if you know the radius of the star by by some other method like luminosity method and all those things and modeling, and so the period, every period, you can also get the period of the planet going around the star by measuring repeated drops, and you can if you observe three drops, consecutive drops, then you can determine the period in terms of days. Okay, so and this is what the equation shows. Okay, now I will come to radial velocity technique. This technique actually is basically talks about the Doppler wobbling, which means that that as you can see here, we all know that the planet goes around the star, but actually planet is going around its common center of mass in the star planet system, and the star is also going around the same common center of mass system. However, since because the planet mass is much smaller than the star mass, so therefore the center of mass is very close to the center of the star. So the star actually wobbles while the planet goes around the star. So if you do very precision spectroscopy, you can actually measure the amplitude of this wobbling. The amplitude will give you the m sin I, and the period will be given by the uh, by the repetition of the radial velocity oscillation. So with both these together, and with the if it also happens to transit, that those 2% of the stars which may have a planet, and if this transits, then putting this together, you can actually know the mass of the planet, the radius of the planet, and so therefore you can actually know the density of the planet, and you can determine whether the planet is gaseous or rocky, and have some idea about its structure. Okay. So here is the cartoon example. You can see that the radial velocity simulation, you can actually see that as the star wobbles, its spectral lines in the star spectra also wobbles, and if your instrument is precise enough to determine this wobbling, then you can measure the existence of the planet around the star precisely by measuring its mass and its orbital period. Okay, so in terms of equation, you can give the K1 is the basically the amplitude, and G is the gravitational constant, P is the period. So you have the M2 as the mass of the planet. Sin I is the angle that is subtended between the observer and the sky, and on the sky, the angle that is subtended by the the orbital plane of the planet going on the star to the observer, and m1 is the mass of the planet, a star. So now since you have m1 is much greater than m2, so you can m1 plus m2 is almost equal to m2. So this can be actually simplify the equation into this. So you have K1 as observable, and M2 you can determine knowing M1. M1 you can determine through luminosity estimation as well as from spectroscopy. Spectral line fitting. Okay, now let me try to do the astrometry part, which is also similar to Doppler wobbling measurement. It's basically another way of measuring the Doppler wobble. But before that, I want to make you understand the concept of parallax. You have distant stars. So like if you happen to when you travel by train, okay. So the trees that are closer to the railway track, they move very fast, and the trees that are far away, that are little far away, they move slowly. They happen to move away slowly, and the trees that are very far away, they almost look very constant, like like they're hardly moving. Everyone must have experienced this as a child when you were like sitting on a train and looking outside the window. So basically, this happens because of parallax. So same thing happens. We are on a spaceship called Earth, and it is going around the sun, and the sun is going around the galactic center. Okay, with a very high speed of roughly 250 kilometer per second. Okay, now now what happens is that the stars that are nearby, they seem to move very fast against the background stars that they hardly move. That is what it is shown here. So you have the sun here in the Earth. So these are the 6 months period, 1 year period. So 6 months this position, this star will appear here. This star, for example, nearby star, and and 6 months later, this star will appear here because of the Earth going around the sun. Whereas like the distant stars will hardly move. So this angle you can measure from using the geometry, and from that you can figure out what is this distance. Okay, this is determining those distance, parallax distance, using the method of parallax. Now, how do you put this method to measure the Doppler wobble? So it is like this, that as I said, that you have a Doppler wobble, the star is going around the Berio center, common Berio center, where the planet, you cannot see the planet, but you can actually see the star moving slightly like this. Okay. So now against the background star, if you try to observe the star continuously for a few years, and if you see the stars are simply oscillating around a certain common point of the magnitude of micro arc second or several tens of micro arc seconds, that means there is a planet around it. Okay, now this kind of observations require space-based observations, and this is equivalent of doing Doppler measurements using ground-based spectroscopy. Okay, which I just talked about. So, with these two methods, you can actually measure the mass of the planet. That is either by Doppler wobble spectroscopy or by astrometry. You can measure the mass of the planet. While by doing transit photometry, you can measure the radius of the planet. So now sum up, radial velocity is the only ground-based precise method for measuring mass of exoplanets down to super-Earths. While space or even Earth, depending upon what is your instrument precision. While space-based astrometry with a precision of sub-micro arc second or better can in principle do the same job, but out of scope for the Gaia, which is having 20 to 25 arc second precision limit. So you can do Jupiter's around stars. Okay. In the age of space-based transit photo surveys, it is extremely important to know mass of exoplanet, which is one of the fundamental parameters. Okay, so which means that since we know that there are many transit missions that are happening, that is space telescope, that is Plato, TESS, and Kepler. Kepler happened in the past 2009. Currently, TESS is going on, and in future Plato will come up. So Kepler was the first exoplanet mission that actually discovered, super Earths and Earth-sized planets in very close orbit to the planets. Okay, so now here I will introduce another concept called habitable zone. So what do we mean by habitable zone? By habitable zone, what we mean is the following: is that the planet does not have its own heat. The heat it gets from the star. So distance from between the star and the planet is such that if we consider only irradiation, that is, assume that its atmosphere has similar properties that of Earth's atmosphere. That is, most of the heat is reflected back into the sky. There is not much of greenhouse effect. Then in that case, what will happen is that if we look at and assume that life is similar kind of, if we consider life as similar that of exists on Earth, that is you can see that life existing in underwater volcanoes, even at plus 65 degree or 70 degrees Celsius, like in the form of microorganisms, as well as deep in the Antarctica at minus 50 degrees Celsius, there also microorganisms exist. So if you consider a range of plus 65 degrees Celsius to minus 50 degrees Celsius as the range where organic compound can exist without getting dissociated themselves, dissociated. Because if you heat organic compounds more than 70 degrees, they will start dissociating actually. I mean, they will start breakdown. So therefore, in this region, suppose if you have, a planet where it receives the right amount of heat from the star so that the temperature is in this region, then it is called habitable zone. Okay, you can see that there are some examples of the stars that are today we know about in the habitable zone, but they are not like Earth size. They are much bigger than Earth. Currently, we don't know any planet that is of Earth size going around the sun-like star and lies in the habitable zone. We have not found any, and though we have totally more than 5,500 planets known so far using transit method and radial velocity method, still we have not come across a single system where you have a Earth twin, that is a Earth-like planet is lying in the habitable zone. So you can see that these are you have the y-axis here. You have the star size, and the smaller star will be cooler star, and the larger star will be hotter star. So therefore, the hotter star means the habitable zone is farther away, while in the cooler stars, the habitable zone are close by. And so therefore, you can see that this the blue region is the habitable zone, and You can see the Earth lies very close to the border of the habitable zone, where Mars lies well within the habitable zone, yet Mars is not habitable because it has hardly any atmospheres. Okay, so that's why atmosphere is another thing that one has to take care of. That is, it has too thin atmosphere to actually, block the heat, and so whatever heat it receives from the sun, it immediately is radiated back. So that's why, given a condition similar to that of, Earth's atmosphere, so this is how the habitable zone is actually defined. Okay. So now what are the science motivation for exoplanet searches? First, as I said, that we don't have a Earth twin kind of system so far, and all the planets that are known so far are like this. These dots are the planets that we know so far, and the radial, these numbers, 5 meter, 1 meter, 50 cm, 30 centimeter, and the position of Earth and Mars are here, shows the what kind of precision you require in terms of radial velocity to actually detect these planets. So currently the best instruments can go to like 30 centimeter. We cannot go better than that. So we have some of the detections are close by here, and therefore as we go away in the habitable zone, you can see that detections are almost null. So that is why the new instruments will come up in the future, where we'll probably have new detections in this region. Currently, most of the detections are here, but here itself, such a zoo of exoplanets are opened up, which are very different from our exoplanet, our solar system, that has thrown up open challenges to how planets form around stars. Okay, now I come to, so after giving a basic introduction on exoplanet science, I'll now talk about exoplanet science in India. So originally in India, actually there was not much of work being done in the field of exoplanets. So in 2007, I started this, exoplanet program at Physical Research Laboratory and Ahmedabad. Our institute has a telescope at Guru Shikhar, Mount Abu. So I plan to start a program using the Doppler radial velocity to measure the Doppler wobble around stars to detect any planets. So the program is called as PRL, Advanced Radial Velocity Abu Sky Search. Abu Sky means because the observatory is placed at Mount Abu, so all stars that can be seen from Mount Abu are under the subject of search. That's why Abu Sky Search. So PAROS became operational in the winter of 2012. Okay, so currently we have like 4 telescopes. This is the PRL 2.5 meter telescope. This is the PRL 1.2 meter telescope. We have 43 centimeter telescope. And this is the inside picture of PRL 2.5 meter telescope, and this is the inside picture of PRL 1.2 meter telescope. Okay, so we have PAROS 1 attached to 1.2 meter telescope and PAROS 2 attached to 2.5 meter telescope, and we use transit photometry on the 43 centimeter telescope. Okay, this is the spectrograph layout of the spectrograph, and this has to be kept in vacuum chamber because if you want to, as I showed you that if you want to measure few meters per second, then the instrument has to be stable. That is, if you have a vernier caliper, if you want to measure 0.1 millimeter, then your instrument should be have a a stable have markings that are much better than 0.1 millimeter, maybe 0.05 millimeter or something, right? So similarly, if you want to measure some planet with a K value of amplitude of wobbler with an amplitude of few meters per second, the instrument should have a stability of 1 meter per second or better. Now, to do that, you have to do 2 things. You have to stabilize the instrument in temperature wise and as well as air pressure wise. So, because if there is a change of pressure of 1 millibar in the atmosphere, then the instrument may shift by 100 meter per second. Similarly, if there is a change of temperature of 1 meter per 1 degree Celsius, then there may be a change of shift of instrument drift by 100 meter per second. So therefore, you have to, if you are keeping the spectrograph at 25 degrees Celsius, then the temperature should of the entire spectrograph, which is like typically few meters by few meters, should be around 25 degree plus minus 0.0001 degree Celsius. That is up to 1 milli degree Celsius accuracy you require. Similarly, you have to put this instrument in a vacuum with a stability of, like 0.01 millibar or better than that. So that, like your instrument is stable to a level of 1 meter per second. Now, to make this, it is very difficult, and because large size temperature control at all. But fortunately, at PRL, we were able to achieve this instrument building of stabilized spectrograph. And so, in 2012, this is one of the first slide of PARS data. You can actually see the stellar spectra, how it looks like. So you can actually see the stellar spectra. These are absorption features, one of our lines from the star spectra. And yes, so what we do is that we run cross correlation around these absorption spectra to determine the cross correlation function. That is, we want to determine the Doppler shift. Okay, Doppler shift because of the star global. Now the star is not a solid body. Star is a gaseous body. So we have to make sure that these lines that are absorption lines that are picking up are strictly photospheric, because the photosphere of the star actually co-rotates with the entire star. The corona and the other place will not co-rotate, but the photosphere of the star co-rotates. So we have to choose specifically photospheric lines, that those lines which are arising from the star, from the photosphere, which is say star's typical radius maybe like a couple of thousands kilometers, like say just to scale, suppose your radius is of the order of 10,000 kilometer. Sorry. Let us say it is a 10,000 kilometer, let us say. Then you have the thickness of the photosphere should be of the order of like few tens of kilometers. I mean, in terms of ratio, that is the small thickness of the photosphere. Okay, and so therefore, all these lines are coming from those thin region, and then we choose those lines by putting a mask on the spectra, and then see that how these lines are behaving over time at T1, T2, T3, and that's what is showing here. And then we do the cross correlation. You get the cross correlation function and find out the RV fitted and the lowest point of the absorption feature, the fitted peak, you can say, or absorption peak. And so this is measured from time to time to figure out whether the star is wobbling or not at a level of few meters per second or few centimeters per second. Okay, so typical temperature stability of a PARS-1 is shown here. And I will skip this. So yes, so in PARS-1 we have kind of achieved over a period of 2 years about 1.4 meter per second, which means that we can easily detect Neptune-sized planets. And so, like in 2016, we had this global recognition of our work, in which we had shown that like PARS actually was found to be third most precise spectrograph in 2016, with the best was doing about 80 centimeters per second, where we were doing about 1 meter per second. Even though we were with a very humble 1 meter, 1.2 meter size telescopes, other telescopes were around 3.6 to even up to 10 meter plus class telescopes. Okay. Okay, so now I want to say that why it is so hard to go to sub 1 meter per second or something like that. That is because when you actually image, this is how the starlight is dispersed on the CCD, on a detector, imaging detector like CCD. And these black lines are actually the absorption features. So basically what happens is that if you are trying to, suppose you take this feature which is moving this way or this way, so you basically, like you are trying to see how much it is movement on the detector surface, which is like a silicon crystal. Detector CCD is basically silicon wafer. So basically you are measuring length on a detector surface. So now here is the electromicron photo of a silicon surface where these individual dots are basically atoms, silicon atoms. Okay, so you can actually see this is the scale of 1 nanometer. And then so if you want to detect 10 centimeter per second, so then you have to determine like 1, 2, 1, 1, 2, 3, 4, 5. 5 atom spaces you want to determine. Which means that if you want to detect a Earth-like planet going around a sun-like star, which produce a Doppler bubble of 9 centimeter, that means you have to get down to a level of this level. Okay, and that's where the difficulty comes. So fortunately, we have got down to about 30 centimeter per second now, but 10 centimeters or under 10 centimeters is still a challenging task. Okay, now I'll come to the point that, in 2018, we had the first the exoplanet discovery from India. The source is called K236b and K2236b, and this is a 27 Earth mass planet with a radius of 6 Earth radii and going around 19.42 days around a late F-type star. Okay, and then we had subsequently another very interesting discovery. It's known as like in the solar system we have Mercury, Earth as the most dense planet. Okay, Earth and Mercury actually both are almost same actually. Mercury is 5.4 and Earth is 5.5, whereas this planet, which is the densest and most massive giant star, massive planet, is actually like density of 14.1, and its mass is about 12.89, 13 Jupiter mass and 14 density of 14. So this is till date, this is the most dense planet that has been known to mankind, and it is going around a like slightly evolved sun-like star, and it has a period of I think 7 days. Yeah, 7 days. Okay, so this was also another important discovery with Paras-1. Now, another important discovery that we had with Paras-1 is this hot Jupiter. Again, but in this case, it is a very extremely low density, is 0.28. So you can see that there is a wide variety of exoplanets that exist. One is very high density, another is very extremely low. These are both are of like similar radius. One is 1 Jupiter mass, another is 1.44 Jupiter mass. This one is slightly larger in size, but mass is extremely small, 0.7 Jupiter mass, while the other one was almost 13 Jupiter mass. So therefore this fellow's density is 0.28. So that shows that how the exoplanets, different exoplanets are formed. The environment of formation of the exoplanets around stars are very different from system to system, and understanding them, having a common theory is extremely challenging. Okay, so here I show you PL 2.5 meter telescope and Paras-2 spectrograph. This spectrograph works at a resolution of 110,000 resolution under vacuum. This is a vacuum chamber, and the spectrograph is inside this chamber, and the optical fibers collect starlight from the telescope and bring it to the spectrograph, and these blue fibers that you are seeing are basically the fibers that carry the starlight and the calibration light. Okay, so again science motivation is again the same thing, how to reach this region and detect as many planets as possible that are very similar to Earth, or at least mini Neptunes or 10 Earth mass kind of planets or 5 Earth mass kind of planets. Okay, so I will kind of forego this because this is little bit little tougher for the audience. Okay, this is a photograph of Paras 2 optical layout, and you can see the vacuum chamber is opened up. You can see all the optical components. You can see the E-shell, off-axis parabola, lens barrel, okay, and the detector is here like that. And this is the telescope Paras 2 Cassegrain unit. You can see this pipe coming out. This is the optical fibers coming out of this instrument. The telescope light is focused on the fiber tip. The fiber tips are somewhere here inside this box where the light from the telescope comes and gets focused on that. And this is the layout of that, how, like these are the fibers and this is the optical layout of the gray diagram of the system. Okay, so this is the kind of so this is the kind of temperature stability that we get. You can see that we achieve peak to value as 0.003 degrees Celsius at 24 degrees Celsius, and this is the kind of 1 sigma. This spectrograph is very well stabilized, and so the spectrograph is stable to a level of 30 centimeters per second, and on sky we have like about 2 meters per second. And these are spectra, and so these are some few like sub-Saturn discoveries that we have made with Paras 2 and 2.5 meter telescope. This is another one. These are like 70 to 80 Earth mass in the range. This is the transit light curve, and this is the radial velocity curve, light curve. Okay, now I'll talk of transmission spectroscopy using absorption of starlight through a planet atmosphere. So far I have talked about the planet mass, radius, and the density part and all those things. Now we want to also learn how to, find out what are if there is atmosphere around the planet, and what are the chemical elements that may be present in the atmosphere. So basically what happens is that when the star, you see you have the observer somewhere here, and then you have the planet and you have the star. The planet is going in front of the star as the transiting happens. I talked about the transiting. So some tiny amount of light of the starlight also passes through the atmosphere of the planet as it is shown here. So that gives, like here in detail. So the starlight to the observer, it actually, here's some absorption features because of these clouds, if clouds or whatever atmospheric elements are present in the planet's atmosphere. And if you study in detail that, then you may have a chance to understand the chemistry that is going around the atmospheres on the planet, distant planet. So that is how it is done. So what one does is that now, so far I have talked of one single dip like this, right? So we have a broadband photometry of say like 500 to 900 nanometers, and then you get the dip like this. But suppose I break it into small, instead of 1000 nanometers or 500 nanometers bandwidth, I make it, let us say, 1 nanometer bandwidth, or 10 nanometers bandwidth, let us say. Okay, 100 angstrom resolution. So every 100 angstrom, I want to measure the dip, how the dip is varying. So within that 100 angstrom, if there is some element of strong absorption feature, I will see the variation in the depth. Okay, that's the whole idea. And so the variation of the depth will tell me whether a particular molecular species is present in the atmosphere of the planet or not. So that is what is showing here. Actually, I will change this. Yeah, you can actually see these are like from HST Hubble Space Telescope observations. So these data points are actually observations, actual observations, and you can actually see that and these lines are actually models, and then they have to try to see that okay, you have this absorption feature here. Okay, so you can see the data, one data point is here and another data point is here. So of course this is like 2 sigma kind of detection, but you see from using those they are able to sodium and potassium they have clearly detected. So like that. So so like many of these molecules can be detected like sodium, potassium, iron, hydrogen, water, carbon monoxide, HCN, like that, titanium oxide, like that. Okay, so here is another one, was 70. This is from Hubble Space JWST telescope, James Webb Space Telescope. You can actually see they have detected. So here actually you can see the the solid line is the model, and the data points are actual observation data points from the JWST. You can see that for this around WASP 79b, they have clearly detected water molecules actually. Okay, that doesn't mean that life is there, because these are not, the temperature of the planet is pretty high. The life cannot exist. But these molecules actually exist in terms of vapor form. Okay, I will show that. Yeah, this is another example. You see, so like various transit curves at different wavelengths, like 4.6 to 5.71, 4.19 to 4.6, like that. Okay, 0.9 to 0.5, this is one band. So they have observed this transit. So the variation in the transit depth actually gave them this data points. This transit curves here corresponds to these data points here. Okay, and so the solid line is the model, and then this data point shows that okay, they have got these chemical elements found. Okay, this is, I think, was 36B, I think 39B. Okay, so I will just this is another case, like where they claim that they have determined that dimethyl sulfide thing, but it has been like here is again the model and then the data points. So these are all space-based observations. Okay. So now what is the next? So like in 2039 perhaps we have 37-meter aperture telescope coming up with this thing. So if such a big 37-meter aperture telescope comes and then they look at the elemental compositions of atmospheres of exoplanets, definitely a much better results than this will come, and like Doppler resolved spectroscopy will be also possible. So, but that doesn't mean the role of small telescopes is gone. It's because you don't get large amount of time on large telescopes. You need small telescopes of 2 to 3 meter class telescopes to do the basic groundwork to identify the candidates, to identify the mass of the planet, and then and the radius of the planet, and then once those physical parameters are established, then you select few of them and go to such large telescopes to determine the further studies, to find out what chemical elements on the atmosphere are present and all those things. So with this, I say thank you, and I welcome any questions.